To round out the videos, let's quickly go over some of the highlights in Help and Tips 10, which will be a nice little summary of the two things in the guides, the p-value adjustment and running a one-way ANOVA. All those things are covered in here, and this is using the car data, which is obviously different than the fake example I used in the guides for the heart rate study. So let me just open up my car data here, and it all looks good the way it normally does. And let's start by asking a research question that a basic one-way ANOVA would answer. And we could ask, does the average car price depend on car brand? Or in other words, are there significant differences in price between car brands? So our groups are the different brands of cars. And therefore, our categorical variable of interest is make, with 5 different car brands. So how do we run and check an ANOVA to answer this question in R? Well, the way I like to do it is to just set up my regular linear model the way we always do. Price is my response, and I have a categorical variable of make. I can run that model, and then to actually assess the ANOVA results, I referenced the Anova command. You've seen it, you've used it a few times, and you've started to see what the table looks like. Well, now we're going to formally look at the Anova table, which is on page 233 in the book, and I've talked, I think, a little bit about before in previous weeks. So we just do Anova and then the name of our model. What this gives us is what is called an analysis of variance table. Quite simply, to answer our research question, all we need to do is look at the p-value on our make factor, our make variable. In this case, it's statistically significant. Therefore, I know that the make variable is statistically significant in explaining some price differences on average. From an ANOVA study design standpoint, I know that there are average price differences between each of my car brands. Here's the trick. This doesn't tell me which car brands are statistically different from one another. So if I look at which car brands I have Buick. Let me get this up here. I have Buick, Chevrolet, Pontiac, Saab, Saturn. These results, this p-value on this make category does not tell me which of these brands is significantly different from one another. I just know at least one of them is significantly different from another one, or at least the grand mean of all of them. The average price are all of them together. But really, that's it for running a basic ANOVA. And again, go through the guides, go through bit by bit what each of these things are, and how we make this determination. But in R, this is all it is. There's another way to do this in R, and instead of using the LM function like we've been using all along, you can use the AOV function and then just specify the the response variable and the explanatory variable, and you can store that as some AOV model instead of our usual LM model. And I can use the summary command on this AOV.1 model, just like we do on the summary of LM.1. And it shows us the same thing. I like to do the LM version because if I want to look at, say, regression coefficients later on, I can do that. And as you've seen with categorical variables, it kicks out one of the groups when providing those coefficients. So you might start to think, well, wait, can't we get pairwise comparisons here? Because it's comparing each of these to a reference group. Sort of, yes, you could get some of the pairwise comparisons, but not all of them. We'll make the formal connection between the regression output and the Anova output in a few weeks. But for now, this Anova table, that's really all you need to focus on. Sums of squares, mean square, an F value, and a P value. Pretty straightforward. Now we can check our assumptions. I put in, technically, one of the assumptions is that the mean of the errors is 0. But that's always true by default, the way we fit our model. So there's nothing, I'm not going to have you ever check the mean of your errors. It will always be 0 by the way we fit these things. But we check independence just like we did in regression. We just ask, is the price of one car going to influence the price of another car? So that's the same. Checking the normality of my errors is the same. I can check a histogram, a box plot, QQ plot. Obviously, I'm violating some normality here, but there's nothing new there. Bad normality, but I still check normality the same way. And now for checking constant variance of errors or of the groups, our traditional way was to plot the predictions and the residuals. Let me do the standardized ones. And then assess whether or not the residuals were evenly distributed above and below 0. But when we do an Anova, we have these nicely separated groups. So I can do a nifty little trick for checking assumptions, for checking the constant error variance or checking the constant group variance. If I open the psych package, I can use the describe by function to say, give me the statistics on price, car price, as split by each car make. It then nicely gives me the car statistics on price across each car brand. And to check the constant variance assumption, I simply look for the largest standard deviation, in this case 6901, and I look for the smallest standard deviation, in this case 1827.9. And I take their ratio. I just take the ratio of the standard deviations, largest and to smallest. In this case, it's 3.77. For our purposes, it's greater than 2. 2 is our arbitrary cutoff. So we say this fails the constant error variance or constant group variance assumption. So that's it. Pretty straightforward. The last thing we can do, and this is where we got into it, it's a little crazy part of the all possible group comparisons. If I want to check to see which of my groups are actually statistically significantly different from one another, one way is to use the pairwise.t.test command. And I just specify my response variable, my explanatory variable, and like I talked about in the other video, a p-value adjustment approach. In this case, I'll use the Bonferroni adjustment. And I run that, and it gives me this grid. And this grid has most of the groups on one axis, horizontally, and most of the groups on another axis, vertically. And then when I look across them, when I look at the intersection of the top and the side, these are the p-values corresponding to whatever cell is being intersected. So this cell right here, this 0.0015, is the p-value between Chevrolet and Pontiac. And I can go through and look to see which values are statistically significantly different or not. And as you see here, all of these are statistically significant. Every single one. All these p-values are below 0.05, and some of them are quite small. Well, that's great, but that just gives me the p-value. What if I want to actually see what the mean price difference is? This is where the GLHT function comes in. And I very much encourage you to read through that p-value adjustment to see each of these parts. But I won't belabor that point here. Oh, I didn't want to do that. I already have it installed. Let me see if I can. Well, it's going to freak out for a moment. Okay. So I already have you need the mult comp package. And, okay, so it's going to install. Sorry, I didn't mean to hit that. We'll get the mult comp package and open it. Okay, it's giving me a bunch of warnings. I don't care. It's still going to work just fine. And all you're going to do to look at these pairwise comparisons is you're going to use the command glht, the name of the model, and then this right here will not change. You're going to use the command, the syntax ln fct equals mcp. In easier words, this is saying, give me some linear factors, and I'm going to give me some linear, we're looking at a linear comparison, and I'm going to do multiple comparisons. The only very particular thing to specify is our grouping variable, make. So I specify the name of the model, and I specify the grouping variable, make. All the rest of this stays the same. And this thing equals Tukey is just saying compare all possible direct mean differences between my groups. Tukey just means give me all my possible mean differences of one group minus another group. And so I'm going to call this whole thing glht.1 and run that. And when I want to look at the results, I just do summary. I specify the name of my model, my GLHT model, and I again use a p-value adjustment. And this time I'm going to use the Bonferroni p-value adjustment. And voila, magic. Gives me every single brand comparison. Chevy minus Buick, Pontiac minus Buick, ... Gives me the average price difference. Gives me the standard error used in that calculation, the t-statistic, and the p-value on that comparison. And it tells me down below, oh, you use the Bonferroni method to inflate your p-values to help combat the type 1 error rate in multiple comparisons. So that's great. I may ask you, I won't ask you to do anything super crazy with this. At most, I just ask you to just like copy and paste something like this and run it. But this lets you have full control. And you can look at even more. You can look at the confidence intervals for each of these comparisons. We can get it's got to think. Oh. We can get a confidence interval for what this mean difference, what the true population mean difference is between these populations. Between these brands. And it doesn't look great. You've got to change the settings a little bit, but you can actually plot these confidence intervals to see which ones overlap 0, because if they overlap 0, if the confidence interval overlaps 0, then we know that that we do not have evidence to reject the null hypothesis because it includes 0. But this doesn't look great, so I'm not going to ask you to do this. It's just kind of fun to play with. Again, our different p-value adjustments are all in here. Holm, Hochberg, Hamel. I'll have you play with those later on. And lastly, I used make equals Tukey above. You can create all your custom contrasts in advance. All your custom comparisons in advance, as I will call them. Here I call them contrasts. But you can go through and define any possible comparison you want to make. And then you just drop the name of those comparisons back into this command. It'll show you the same thing. So that's it.